Okay, let's go ahead and get started, folks. Um, so yesterday, I apologize. It went a little bit longer than I was hoping it would go. I guess with all of the um, introductory stuff, where I'd share with you what we're going to be doing on the online course, that seemed to carry a little bit longer than I was hoping it would carry. But hopefully, you were able to watch the video okay yesterday. Hopefully, you were able to get some things. Hopefully, you are aware now of what we'll be doing with the material here, or how we'll be conducting the class. So, I think if you're, yeah, I think moving forward, it should um, be fairly smooth, I hope. If there are any issues, then please make sure, again, let me know. I will be available. You can contact me through comments in Google Classroom, email me, and let me know how things are going. I think this will work out the best for you guys, because I think this way, then, if there's any issues with connectivity, if things get cut off, if there's any technical issues, you won't have to worry about disrupting our meeting. I think also this way it allows you to watch the video at your pace. You can rewind and see whatever you missed, or go over something that you may not have understood the first time. And so I think this will work. Let me know through Google comment, and let me know how you feel about it, and what we can do to make the changes to make it run more smoothly. Okay. Um, no news, nothing new to share with you. I think at this point, the plan is still that we will continue with the online lessons until March 31st. I think that's at least what I've been told so far. So I think we'll move forward with that. Okay. All right. So I didn't see anyone yesterday afternoon at our tutorial. Again, make sure you remember I will be available to meet with you live after school, 3:15 to 4:15, or 3:15 till whenever all the questions are answered. Make sure you let me know if you have any questions on the homework or any questions on the material that was covered. Make sure you let me know. Okay. All right, then let's go ahead and let's quickly review what we left off with yesterday. We were talking yesterday about the dipole moments. We were talking about how dipole moments are set up. We talked about how the electronegativity differences within between the two atoms of a bond will set up a polar bond itself, and the polarity of that bond will, when taken into consideration with the geometry of the molecule, will determine then whether that molecule has a dipole moment. Okay. We'll talk much more about geometry later on in the chapter when we deal with VSEPR, but yeah, hopefully you remember quite a bit from last year when we talked about geometry, electron and molecular geometry. There will be a PhET lab that I'll ask you to do later on that will allow you to practice the determining the geometry of atoms. Okay? But again, like we said, if we have two atoms that are bonded together, if they are the same atoms, then we can expect then that the electronegativity difference there would be 0. And so therefore we would have here non-polar bond. This would be a non-polar bond between those two atoms. If the two atoms that are connected together are different, okay, and the difference in their electronegativity is about let's say 0.1 through 0.3, we still also have then a non-polar bond. Okay, so that's also a non-polar bond. Okay, if the difference here between these two is about 0.3, is between 0.3 to about roughly 2, we're going to consider that a polar bond. These will be polar bonds. Okay, and then finally, if the electronegativity difference is greater than 2, then we consider this bond then an ionic bond. Okay, so that's what we talked about yesterday. Okay, then we talked about how with a polarity difference, okay, the electrons tend to move towards the side that is towards the atom that is more electronegative. And in this case, then if Y is more electronegative, electrons will move towards that side of the bond, making the bond itself a polar bond. That polar bond then leads to an aggregation of electrons in the molecule as a whole. Okay. The electrons then will move gravity towards the Y side of this bond, and therefore the molecule itself then will have a accumulation of negative charges on this side of the molecule, and setting up then a dipole in this molecule. So dipole meaning then two poles in this particular molecule. And so this molecule has then a dipole moment. Yep. And this, again, this dipole moment, remember, with these molecules, we can pick up on this dipole moment. You set the molecule within an electrical field, switch it on so that one side is going to be positive, one side is going to be, I'm sorry, let me flip that around. One side is going to be negative and one side is going to be positive. The molecule itself will flip around so that the positive end of the molecule will be pointed towards the negative electrode, negative end of the molecule will be pointed towards the positive electrode. That's how then we can determine the polarity of that molecule, that it has this dipole moment. Okay, so this is a linear molecule. So the accumulation of electrons towards one side versus the other will set up this dipole moment. But we saw then also with water, which is not a linear molecule. Remember, water from first year chemistry is a bent molecule. It's bent, it has a bent geometry. Because these two lone pair electrons push down on it, the angle here then is roughly about 104, 105 degrees. And so the bond here, each one of these bonds will also be polar with the electrons moving towards the oxygen. If you think of this molecule as a whole then, with the two lone pairs here and the electrons moving towards the oxygen, this side of the molecule, the oxygen side of the molecule, will have an aggregation of negative charges, and the opposite would be true then for the hydrogen on the hydrogen side. And so you set up a net dipole moment that moves towards the oxygen as well. So this molecule then, water molecule, has a dipole moment. Okay? And if you notice here, this is not a linear, but this is a bent geometry. So make sure you understand that we'll talk about this in just a moment, but the geometries of the molecule will also help to determine whether the molecule will have a dipole moment or not. So there will be two key factors you have to keep in mind as we move forward in the discussion of polar molecules. First, make sure you determine whether the molecule has polar bonds, because that has to happen. And then the geometry of the molecule will also determine then whether the molecule then has a dipole moment or not. Okay. So that's how we will determine then, and we'll go over this, whether a molecule has a dipole moment or not. All right, let's take a look at, so there's water, we talked about that. Let's take a look at a molecule like ammonia. Okay? So to make this determination then, we have to make sure we are ammonia. So we have to make sure we remember how to draw the Lewis dot structures. I will review this with you a little bit more towards the end of this chapter where we talk about geometry, but hopefully you remember this from our discussion of first year chemistry. Okay? So ammonia, so make sure you can draw these Lewis dot structures. Okay? So let's take a look at ammonia. Lewis dot structure for ammonia then. Nitrogen has 5 valence electrons. Okay, so let's go ahead and draw that in. Okay. Hydrogen has 1, so therefore hydrogen will form a single bond. 3 with nitrogen. So the nitrogen then will have 3 single bonds with each one of the hydrogens themselves. Okay. Now, with that said, then we got to make sure, remember, there are 4 electron domains here. So since there are 4 electron domains in this particular, for the center atom of nitrogen here, you have then a tetrahedral configuration. So it's going to be tetrahedral around the center atom there. Meaning then, if we want to take a look at this, okay, and we'll draw this as a dashed line structure. Okay. You're going to have then these two roughly on a plane. All the bonds then will be on opposite planes with one another, with one coming up and one coming back. And this is what we call the wedge and dashed structure for ammonia. You can imagine then these two are on the same plane, and then you have one hydrogen going back and one hydrogen coming up out of the plane of the page there, with the angles then between each one of these bonds, with each one of these electron domains being roughly about 109 for the tetrahedral geometry. Okay. All right. So with that said, then and so to simplify matters just a little bit here, you can imagine then that each one of these bonds then will be polar. with the electron density moving towards the nitrogen. Okay, and then on top of that, you have this lone pair here, and you can imagine that if that is the case, the electrons will accumulate around the nitrogen, setting up a partial negative charge around the nitrogen and partial positive around each one of those hydrogens, setting up a net dipole moment that moves and points towards the nitrogen. So therefore, ammonia then becomes a polar molecule. So ammonia is going to be a polar molecule because of that. Okay. Yep. All right. So if you take a look at ammonia here, just like I've set up for you here, if you notice then each one of those. So there is your tetrahedral configuration for electron geometry. What we call this then is a trigonal planar molecular geometry. We've talked about that. Each one of the hydrogens then will, hydrogen ends will have a partial positive charge because the electrons move towards a more electronegative nitrogen. The accumulation of negative charges will be around the nitrogen. The net dipole moment then will be towards the nitrogen to set the ammonia molecule in an electrical field. And again, then the negative side of the molecule, which is nitrogen, will point towards the positive electrode. The positive side of the molecule, which is the hydrogen, will point towards the negative electrode. Okay. And if you look at the electron density map here for ammonia, the areas of higher negativity will be highlighted red, and you see then that that area is centered around nitrogen. Okay. So therefore, we see then that ammonia has a net dipole moment that we can look at there. Okay. All right. Let's continue on then, and let's take a look at what's going on. So understand the geometry will determine whether the molecule will be polar or non-polar, so whether there is going to be a net dipole moment or there will be no net dipole moment. And so understand there's two factors. I pointed this out to you. There's two factors to determine whether a molecule will have a net dipole moment or not. The molecule has to have a, first of all, you have to have polar bonds. And then secondly, the geometry also matters. So let's go ahead and let's take a look at an example, okay, of a molecule that has polar bonds, but because of its geometry, there's no net dipole moment. So we have here carbon dioxide. Let's go ahead and take a look at, draw the Lewis dot structure for carbon dioxide. Carbon dioxide, remember, is a double bonded carbon oxygen atom. Okay. The Lewis dot structure for carbon dioxide will look like this, okay, with each bond here being polar, with the electrons moving towards a more electronegative oxygen. Okay. All right. So if you take a look at this molecule as a whole, okay, if you take a look at this molecule as a whole, there's going to be a positive charge around the carbon and negative charge around each oxygen. Now, if you notice here, the negative charge is here around each oxygen, then there is no dipole, there is no two poles here, because each end of the molecule here is occupied by a negatively charged oxygen atom. Each end of the molecule is negatively charged. So they're not oppositely charged. Therefore, there is no two poles, no dipole in this molecule. So this molecule here has no net dipole moment. And again, let me just make sure I reiterate this to you. There is no net dipole moment because there is no dipole. Dipole, by the nature of it, just think about the word. Dipole means two poles, and again, two opposite poles is how we've seen this. If you look at this molecule here, if you look at carbon dioxide, each side of the molecule is negatively charged. So there is no dipole. Each one are negatively charged. The other way you can think about this in terms of these vector arrows is that these vector arrows cancel each other out, so therefore you have no net dipole. I think for you folks who have not taken physics yet, just think of the molecule as having no net dipole because there are no, each end here has no, there are two oppositely charged ends. Okay? But to have a dipole, to have a net dipole, you have to have two ends that are oppositely charged. Okay? So make sure you keep this in mind. In order to get a net dipole moment, you must have two oppositely charged ends. And if you don't have that, you will not have a net dipole. You can think about the net dipoles in terms of vector arrows like we have here, but I think this would be the easier way to go about remembering whether a molecule has a net dipole moment or not. Okay, for those of you folks who are familiar with how vectors cancel each other out, and go ahead and think about it in that ways. Okay? But if not, I think this would be the easier way to remember whether a molecule has a net dipole. Okay. All right. So taking a look at some examples here. If you have a molecule with a linear configuration, and this is the molecular geometry. If you have a molecule with a linear configuration, you're going to notice then that the molecule itself will not have a net dipole moment. Okay, the vectors cancel each other out. An example is carbon dioxide, which is what we just went over. If the molecule has this trigonoplanar geometry, where the angle is at 120 degrees from one another, again, what will happen is that these vector arrows will cancel each other out. In a moment, you're going to see an example here where, if you think about it, then again, what will happen here is that the charges on the outside of the molecule will all be the same. So because of that, again, no dipole, so no net dipole moment. So I'll go over that with you in just a moment here. An example of this would be sulfur trioxide. And finally, if the geometry is tetrahedral, and the same thing, if it's tetrahedral, and again, if you have then negative charges all around the outside, then you have then no net dipole moment as well. An example of this would be the carbon tetrachloride. Okay. All right, so what you need to consider when you determine whether a molecule has a net dipole moment or not, you want to determine the polarity of the bond, and that's based on electronegativity differences. Okay. And then also the geometry of the molecule itself. Okay. Let's take a look at some examples here. Let's take a look at 3 examples here, and let's work through this. Okay. So first of all, let's take a look at hydrochloric acid. I'm going to switch down here. Okay. So the first example then asks us about hydrochloric acid or hydrogen chloride and whether it has a net dipole moment or not. Okay. So let's draw the Lewis dot structure for hydrogen chloride first. Okay. So we have then the molecule here, which is hydrogen chloride. Hydrogen then will be connected by a single bond to chlorine. Chlorine then will have its 3 lone pairs. Okay. The bond here is polar. The bond here is polar because the chlorine is more electronegative than the hydrogen. Okay. And if you can imagine that, chlorine here also has 3 pairs of electrons, okay, which makes this side of the molecule then very negative, leaving the hydrogen side here positive. So because this is a linear molecule, linear nature with an accumulation of negative charges around the chlorine and a deficiency of electrons around the hydrogen, we have then a dipole setup. Hydrogen chloride then has a net dipole moment. So it does have a net dipole moment. Okay, so make sure you are familiar and comfortable drawing these molecules. Okay, so let's go ahead. Let's take a look at the second one, sulfur trioxide. Okay. So sulfur trioxide, let's go ahead and draw the Lewis dot structure for sulfur trioxide. Sulfur then is going to have a double 6 electrons, 2 pairs. Okay. Oxygen, and I'm going to draw this around. Okay. I think you can imagine this first and foremost. Okay. You have then these 2 bonds pairing up to form an electron, form a double bond here. I'm purposely leaving this blank for right now because you're going to imagine this here, that a coordinate covalent bond forms here between sulfur and oxygen, and the sulfur and oxygen here. Another coordinate covalent bond will form, forming 2 single bonds. And so therefore then you'll see that sulfur then will have a double bond, 1 double bond with 1 oxygen here. This oxygen then will have 2 lone pairs, and then a single bond with each of these oxygens, with the oxygen on the top and the oxygen on the bottom. So that's the Lewis dot structure for sulfur trioxide. This is a sulfur here then is going to have a trigonoplanar geometry. It has 3 electron domains around it, so therefore it's going to be trigonoplanar. Angles here then will be about 120. If you can imagine this then, the bonds here will be polar with the electron favoring the oxygen side, which means that for this bond here, for this particular bond, the charge accumulation will be towards the oxygen. For this bond here, you'll also see charge accumulation around the oxygen, and this bond here, charge accumulation around the oxygen. But taken as a whole, if you look at the molecule as a whole, then okay, there are only negative charges around the outside. There is no charge separation, no charge difference. So this molecule here, sulfur trioxide, has no net dipole moment. Okay, and you can see that from the geometry of the molecule. So this is a molecule that has polar bonds, 2 single polar bonds and 1 double polar bond. But because of the geometry being trigonal planar, there is no net dipole moment. There is no dipole that's set up at all around this molecule. Okay. All right. Let's go ahead and take a look at the last one, dihydrogen sulfide. Let me go ahead and erase this, and let's go ahead and draw that one. We have then dihydrogen sulfide, H2S, and again, let's draw the Lewis dot structure here, dihydrogen sulfide. Okay, we have sulfur with its 6 electrons. Each hydrogen then will situate around the sulfur. And to draw the dashed form of this, we can see then that sulfur will have 2 single bonds with hydrogen, making this look very much. So if you look at this, this molecule here looks very much like water. Okay, and so therefore, this bond here will also be polar. This bond will also be polar. There will be negative charges accumulating around the sulfur, positive charges around the water. I'm sorry, hydrogen. So that the sulfur side of this molecule then will have a aggregation of negative charge, and the hydrogen side positive charge. So seeing this, then we see then that the molecule is going to have a net dipole moment. So we'll have a net dipole moment here, okay, because we have 2 polar bonds, and that the structure, the molecular geometry here is going to be a bent configuration. Okay. So these 3 examples then clearly show us then that what we have to consider to determine whether a molecule is going to be polar or non-polar, or whether it has a net dipole moment or not, is the geometry, as well as the whether the molecule has polar bonds or not. If the molecule has no polar bonds, folks, then you will have a non-polar molecule, no net dipole. Okay. All right. So what I would like you to do then, take about a couple minutes. I want you to indicate whether these 2 molecules here have a net dipole moment or not. What I'd like you to do is to try drawing the Lewis dot structures like I did in the previous example for you. And then tell me whether these molecules here will be polar, if they will have a net dipole moment or not. Okay. And I would ask then if you can remember, indicate the geometry as well. So indicate the geometry, if you remember it, of the molecule there. And when I say geometry, I'm referring to the molecular geometry, not the electron geometry. So go ahead and try that, and then when you get back in about a couple minutes, we'll go over. Okay, so go ahead and draw your structures and determine whether the molecules have a net dipole moment or not. Okay. Okay, let's go ahead then. Let's take a look at chlorine. Okay, so chlorine is Cl2. I think you can probably pretty much see this already, whether you'll have this or not. The chlorine then, 2 chlorine molecules will share a single bond between them. You'll have then the 6 valence electrons around, the 6 lone pairs around each chlorine. Folks, the bond here is going to be a nonpolar bond. So the bond itself already is nonpolar. So we really don't need the geometry here to determine this. If the bond is a nonpolar bond, like I already told you, and it only shares a nonpolar bond, the molecule itself will then will not have a dipole moment. So no dipole moment here. So no dipole moment for this particular molecule. Okay, so let's hopefully you see that here. The reason why it has no net dipole moment is just the bond itself is nonpolar. But going forward, then hopefully you realize then that this bond, this molecule is linear. It has a linear geometry. But again, the bond here is a nonpolar bond, and because it's a nonpolar bond, this is going to be a nonpolar molecule, meaning it has no dipole moment, no net dipole moment. Okay. All right, let's take a look at the second molecule then. We have carbon tetrachloride. Okay. Drawing the Lewis dot structure for carbon tetrachloride. If we draw the two-dimensional structure here, we're going to see then that the carbon shares a single bond with each one of the chlorines. Sorry, chlorine, not hydrogen. I'm sorry. I'm sorry. It's not carbon tetrachloride. I'm going to go ahead and erase this really quickly. It's methane. So let's go ahead and erase this. Sorry, first time. Okay. It's going to be methane then. So therefore, the carbon shares a single bond with each of the hydrogens. Electronegativity difference is going to force the electron to move towards the carbon rather than the hydrogen. Okay, and so if you set it up this way as here, sorry, that was the alarm telling me that I need to finish up here. But if you take a look at this here, then there will be an accumulation of positive charges, okay, around each one of the hydrogens, okay, and that there'll be negative charges on the inside around the carbon. But as such, then if you take a look at the outside, there is no difference in charges. You just have 4 positive charges on the outside. So even though you have here slightly polar bonds, so these bonds are polar, they are polar bonds, okay, there is no net dipole, no net dipole moment, because of the way that the charges separate themselves around this molecule. So again, on the outside of the molecule, on the hydrogen side, you have then just all positive charges. There's no negative charges here. And so therefore, this is going to be, there's going to be no net dipole moment set up here. Okay. Now, and so like I said, I'm sorry, the geometry of this molecule then is going to be tetrahedral. Obviously, this two-dimensional structure doesn't show us that, but this is going to be a tetrahedral geometry. Okay. One quick last example here. Let's just change things up just a little bit. Okay, and instead of all hydrogens, replace one of the hydrogens with the chlorine. Let's take a look at how that looks. Okay, so let me go ahead and erase this here, and let's take a look at what happens there when we replace one of the hydrogens with the chlorine. Okay, so we're looking at this molecule right here. Okay, all right. So again, we'll draw our structure: carbon with hydrogen, carbon with hydrogen, carbon with hydrogen, and the carbon with chlorine. Okay. Electronegativity difference in that direction. So electrons move towards the carbon here, electrons move towards the carbon here, electrons move towards the carbon there. But for this bond here, chlorine is a more electronegative atom, so the electron is going to move towards the chlorine there. Okay. Furthermore, chlorine has these lone pair electrons. And so if you can imagine, if you look at the molecule as a whole, you're going to have a positive charge here, positive charge here, positive charge here, but a negative charge here. Okay. And so do you see here then, folks, there is a dipole, there is a dipole that was set up here with the negative charge on this end of the molecule, I'm sorry, positive charge on this end of the molecule, negative charge on this end of the molecule. And so this particular molecule then will have a net dipole moment, making this molecule then polar, because this is a polar molecule. Okay. Okay, so please make sure you write that down and submit the work. I'm running low on time here, so what we're going to do tomorrow, so that finishes up with our discussion of polar, nonpolar molecules. What I'd like to do tomorrow then is we're going to start our discussion then of stability of the compounds and electron configurations. Okay, so please make sure you take a look at that. And I will post a couple problems for you to do in just a moment to finish out this session here. But hopefully today then you can finish up, you'll be able to finish up with the lecture material and not worry too much about the time. Okay. All right, folks, so I will see you again tomorrow morning, and good luck with everything. And if you have any questions, like I said, please make sure you email me, comment through Google Classroom, or meet me after school today at 3:15 to 4:15 at our Zoom class. Okay. All right, I'll talk to you folks tomorrow.